तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This course is about discrete mathematical structures. It is a theoretical course intended for BTech or BE students in computer science in the second semester. And what are the things we are going to study in this subject? So, first of all, what is discrete mathematics and what are the topics which are to be covered here? Discrete mathematics is a study of discrete structures which are abstract mathematical models dealing with discrete objects and the relationship between them. The discrete objects could be like sets, permutations, graphs, FSA, etc. We will see in a minute what are the topics which are to be covered here. And why do you want to study discrete mathematics and why should one study this subject? The reason is in many fields in computer science, basic mathematical concepts will be used, and in any books on them, when such a concept is introduced, they will not explain it in detail, but briefly mention a few lines about it. But for a student to understand the subject completely, that may not be enough. At the same time, one need not go into depth in these subjects also. One should not learn or one need not learn these subjects as a mathematics student would learn algebra or analysis. You want to know something about each topic to a decent depth, and that will help to understand the other subjects in computer science in a better way. The aim of this course is not only make people learn about these topics, but also develop the habit of thinking mathematically. The student should develop to think in a mathematical manner. That is the aim of this course. What are the applications or what are the fields in which these concepts will be used? There are plenty. In fact, in each and every subject in computer science, somewhere or other these concepts will be used. For example, when you want to study programming, after writing a program you would like that it is correct, you want to prove it. So, proving programs correct is a topic which will be studied in this course, which will help you to write correct programs. And in artificial intelligence, a lot of ideas about logic will be used. Prolog is a logic programming language where the resolution principle is used, and we will learn about these in this subject. And in computer networks, lot of concepts about graph theory and finite state automata are used. So, that will be very useful there. In fact, you can find that in any field you will have a few concepts from discrete mathematics which will help you to understand that subject in a better manner. In compilers, you will learn to finite state automata concepts will be used, grammar concepts will be used, hash functions will be used, and these are studied in this subject. And now what are the topics which will be covered in this subject? We will be studying about logic, sets, relations, then functions, graphs, combinatorics, recurrence relations, algebras and FSA. The layout of the subject will be like this. First 9 lectures will be devoted to logic and its applications. Then 3 lectures will be on sets. Actually, this subject does not presuppose any prior knowledge from the student except a reasonable mathematical maturity expected of a high school student. That is the only thing we assume and proceed with this subject. In fact, after learning this subject, the student should be able to think more mathematically and also should have acquired a basic knowledge about these topics. Then we go on to relations. In relations, first we have lecture 13, then afterwards we shift to graphs from lecture 14 to 17, then again come back to more properties of relations from 18 to 23. Then the last lecture will be about lattices, which is also about partially ordered sets. We will learn about certain basic facts about graphs in lecture 14 to 17. Then we learn about functions in lecture 24 to 26. Then a few lectures on combinatorics where we will be studying about pigeonhole principle, permutation and combination and generating functions. Recurrence relation is another topic which is of importance, especially in algorithmic analysis. We spend 3 lectures on them. Then algebras we will study a little bit, where we study about groups, semigroups, rings, etc. And about finite state automaton, we have 2 lectures where we study only the basic principles of finite state automata. We shall give some reference books for the subject. Some of them are new, some of them are old, but there have been recent editions of them. Elements of Discrete Mathematics by C.L. Liu, and the second one is Discrete Mathematical Structures with Applications to Computer Science by Tremblay and Manohar. These are standard books. Discrete Mathematics in Computer Science by Stannard and McClister is another book. Discrete Mathematics and its Application by Rosen. Logic and Discrete Mathematics by Grassmann and Tremblay. This has some concepts about prologue and application of logic to that. Introductory Combinatorics by Brualdi. For topics on combinatorics, this book can be used. Modern Applied Algebra by Birkhoff and Barty. It is an old book, but it has got some good concepts about lattices, finite state automata. Mathematical Theory of Computation by Manna. This book will be useful for proving programs correct. Introduction to Combinatorial Mathematics by Leo. This is an old book, but still it has got some very good topics: permutation, combination, generating functions, recurrence relations, etc. Then for automata theory, this book can be used. Introduction to Automata Theory, Languages and Computation by Hopcraft, Motwani and Ullman. These are only a few books. There are so many other books. Any student studying this subject can use the prescribed book by the respective university or college. Now we shall go on to the first topic, logic. Logic is a very useful topic. Every student in computer science should learn this topic because it is applied in proving programs correct, in databases where you study about relational algebra and relational calculus, and also in artificial intelligence about reasoning and things like that. So, first coming to logic, there will be 9 lectures on logic. They are divided like this. The first 2 lectures will be devoted to propositional logic, then we go on to predicate logic, then logical inference, then resolution principle, then methods of proofs, normal forms, and one lecture on proving programs correct. So, let us start first with logic and propositional logic. What is propositional logic? So, for that first we have to start with what is a proposition. In English language, we talk about sentences, we talk about assertions, we talk about orders, questions and so on. What is a proposition? First of all, it should be an assertion. An assertion is a statement. It is different from asking a question or giving an order. A proposition is an assertion which is either true or false, but not both. So, you must be able to associate a truth value with an assertion. Truth value, the truth value will be false or true. Usually you denote it by false by 0 and true by 1. So, any sentence, any assertion to which you can associate a truth value is called a proposition. Consider the following examples. The following are propositions. 4 is a prime number. It is an assertion, but it is a false statement. So, the truth value associated with 4 is a prime number is false. Then take the next sentence, 3 plus 3 is equal to 6. Again it is an assertion and it is a correct statement. So, the truth value associated with that is true. The moon is made of green cheese, or the moon is made of cheese. This is again an assertion and a wrong statement. So, the truth value associated with that is false. Let us see what are not propositions. Consider the statement x plus y greater than 4. Is it true or false? It depends on what value you are going to give for x and y. If you give x the value 2, y the value 2, then 2 plus 2 is greater than 4 is not correct. Or if I give the value x is equal to 3, y is equal to 4, then it takes the value 3 plus 4 is greater than 4, that is 7 is greater than 4, which is correct. So, depending on the value you give for x and y, the statement takes a true or a false value. It does not have a unique value, it depends on the value you are going to give for the variables x and y. X and y are called individual variables. So, you cannot associate a unique truth value to this. Next, take the sentence x is equal to 3. Here you find that you cannot associate a truth value to this. If you give the value 3 to x, it will be true. If you give some other value to x, it will not be true. So, again this is not a proposition. Take the next one, are you leaving? This is not an assertion. A proposition should be an assertion. Are you leaving is a question and it is not an assertion. So, it is not a proposition. Take the next one, buy 4 books. This again is not an assertion, it is an order. Go and buy 3 books. This is an order and not an assertion. So, it cannot be a proposition. So, whenever something is not an assertion, it is a question or an order, it cannot be a proposition. But in special cases there can be assertions which are not propositions. For example, consider this sentence. This statement is false. This is an assertion. Is it a proposition? It is not a proposition because you cannot associate a truth value to this. If it is true, it is false. If it is false, it is true. So, you cannot associate a true or a false value with this statement. This is called a paradox. This is called actually a liar paradox. This is called a liar paradox. And such a statement, even though it is an assertion, is not a proposition because you are not able to associate a truth value to that. Just as you have variables, individual variables x and y to which we associated numbers, you can talk about a propositional variables. A propositional variable denotes an arbitrary proposition with unspecified truth value, p, q, r. They are all propositional variables and you can assign a proposition to them. P is just a variable, propositional variable. Just as you assign the value 4 to x, you can assign the value of a proposition to the variable p. Similarly, you can denote these as propositional variables and you can assign propositions as values to them. Then when you have propositional variables or actual propositions also, you can connect them with logical connective. There are several connectives. First we shall study 3 of them: and, or, and, not. Consider the proposition John is 6 feet tall and the proposition Q, there are 4 cows in the barn. Then the compound statement P and Q is John is 6 feet tall and there are 4 cows in the barn. When is this true? P and Q will be true when both P is true and Q is true. So, we have a truth table for them. So, and is denoted by this symbol and the truth table for that will be PQ, P and Q. The possibilities are both can be false or P can be false and Q can be true. This can be true and this can be false and both can be true. These are the possibilities. And both are false, the compound statement will be false. When one is false also, the compound statement will be false. But when both are true, the compound statement will be true. Usually we denote false by 0 and true by 1. So, the truth table will be like this: P, Q, P and Q, 0, 0, 0, 1, 1, 0, 1, 1. And in these 3 cases it is 0, it is 1 in this case. So, the compound statement P and Q will be true only when both P is true and Q is true. In all the other cases it will be false. What about the connective R, P or Q? If P denotes this sentence and Q denotes this sentence, P or Q will denote the sentence John is 6 feet tall or there are 4 cows in the barn. When can you say that this is true? When one of them is true, the compound statement will be true, or when both of them are true also, the compound statement will be true. This is called inclusive or inclusive or and the truth table for that will be like this: PQ, PRQ, 0 0 0 1 1 0 1 1. 0 denotes false and 1 denotes true, and when both of them are false, this is false. When one of them or both of them are true, this will be true. This is the truth table. This is called a truth table for R. And for the unary operator not, P and not P, when the P is false, not P will be true, and P is true, not P will be false. So, what is the statement not P? John is not 6 feet tall. That will be the statement for not P. So, we are studying the operators and or not. There is one more operator called the exclusive or. An assertion which contains at least one propositional variable is called a propositional form. So, when you connect two propositional variables by and or, it is a propositional form. We can also use the exclusive or operator. Exclusive or means the truth table for that will be like this. Zero 1 1 0 1 1. In the exclusive OR case, it is true only when one of them is true and the other is false. If both of them are true or both of them are false, it is false. So, when you say something like that, John is 6 feet tall, there are 4 cows in the barn, both can be true, both statements can be true and the compound statement can be true. But in some cases, like say Sudha is wearing a sari and Sudha is wearing a blue churidar or something. And if I say Sudha is wearing a sari or Sudha is wearing a blue churidar, both of them cannot be true at the same time. Only one can be true, the other will be false. So, in such cases you use exclusive or. Usually when you say either this or that, that means exclusive or. When you just say or, it means inclusive or. But you have to be very careful, in sometimes they are used in a slightly ambiguous way. So, when you want to transform an English sentence into logical notation or transform some logical formula into English sentence, you have to be very careful whether you are using inclusive or exclusive or. Usually exclusive or means you must say either or, inclusive or you say just or without that either. And any propositional form, it is connecting variables, it is called a well formed formula. Well formed formula of propositional logic. Well formed formula. It is denoted by WFF, usually called as WFF. So, P and Q is a well formed formula, PRQ is a well formed formula, P exclusive RQ is a well formed formula. So, P exclusive R will be denoted like P exclusive R Apart from these operators, there are two more operators which are used in logic. One is called the implication and another is called the equivalence. What is implication? Let us look at this. P implies Q, it is denoted like P implies Q. In some books it may be written like this, and in some books they rarely use this sort of an arrow for P implies Q. So, when you take a book, you must be clear what sort of a notation they are using. Similarly, not P is usually denoted like this, sometimes it is also denoted like this. So, when you see a book, you must be careful what notation they are using. So, in this case, P is called the premise, hypothesis or antecedent, and Q is called the conclusion or consequence. And what is the truth table for P implies Q? P implies Q, you have 0 0 0 1 1 0 1 1. Then when both are false, it is true. When P is false and Q is true, it is true. When P is true and Q is false, it is false. When both of them are true, it is true. There is a slight problem here. It is not a problem, but you must feel convinced about this truth table. Usually, when we say logic, or what we study is Greek logic, which was formulated by Aristotle, Socrates and Greek philosophers. In such logic, this is the truth table for implication. The antecedent and the consequent need not be related at all. They may be quite unrelated statements, like if the moon is made of cheese, then earth is not round. It could be something like that. There is no relationship between the antecedent and the consequence. But the compound statement is true because this is of the form false implies false. And for that, in the truth table, the first line of the truth table tells you if P is 0 and Q is 0, P implies Q will be true. Greek logic allows that. Usually in Indian logic, you look at the way Aryabhatta or Bhaskara's explanation on Aryabhatta's work, such things are not allowed. Usually the antecedent and the consequence will be related. For example, something like this. This you can very easily see. If I fall into the lake, I will get wet. Obviously, the premise and the conclusion or the consequence are related, and you can see the correspondence between them. But generally in the truth table, you must also give a value to the compound statement even though the premise and the antecedent are not related. So, the implication, this you must remember very well, the implication is true when the premise or the antecedent is false or the consequence is true. It is false only in the case when premise is true and the conclusion is false, or the antecedent is true and the consequence is false. Only in that case it will be false. Other three cases it is taken to be true. This can be read in several ways. You can read it as if P then Q, P only if Q, P is a sufficient condition for Q, Q is a necessary condition for P, Q if P, Q follows from P, Q provided P, Q is a logical consequence of P, Q whenever P. These are different ways of saying this, and you would have studied about sufficient conditions and necessary conditions in high school level, and many theorems where the statement will be in the form if then. For example, you would have studied the Pythagoras theorem. If ABC is a triangle right angled at B, then AC square is equal to AB square plus BC square. So, the statement of the theorem is of the form if something then something. And sometimes you talk about the converse of a theorem, sometimes the theorem will be proved in a slightly different manner. When we study methods of proof, we will go into that in depth. But generally, the converse of a theorem is denoted as Q implies P. P implies Q is a statement, and the converse is Q implies P is the converse, and not Q implies not P is called the contrapositive. So, you have this P implies Q, Q implies P is the converse, not Q implies not P is the contrapositive. So, suppose Pythagoras theorem is if ABC is a triangle right angled at B, then AC square is AB square plus BC square. What will be the converse of the theorem? Converse also you would have studied in school. If in a triangle AC square is AB square plus BC square, then the triangle is right angled at B. So, that is a converse. In this case, it so happens that both the theorem and the converse are true, but several situations may arise where the theorem may be true, but the converse need not be true. Because P implies Q, it does not mean Q implies P is true. Whereas the contrapositive, not Q implies not P, will be true whenever P implies Q is true. Let us draw the truth table and see this. So, you have P, Q, P implies Q, not P, not Q implies not P. So, consider this table. You have the possibilities 0, 0, 0, 1, 1, 0, 1, 1. Another thing is, you must note before going into that, let us see that if there are variables say P, Q, R, S like that, in the truth table there will be one column for each one of the variables, and there will be one row for each assignment of the variable. Each variable can be assigned the value true or false, that is 0 or 1. So, if there are 4 variables, there will be 2 into 2 into 2 into 2, 16 possibilities. So, there will be 16 rows in the truth table. In general, when you deal with n proportional variables and you want to study the truth table involving them, for an expression involving them, there will be n columns. First n columns will be for variables, and later on there will be more columns. Here there are 2 variables, 2 columns are for the variables, and here you consider every assignment, every possible assignment for the variables. So, there will be 2 power n possible assignments of truth values to the variables, and so there will be 2 power n rows and if you look at them carefully, they are representing binary numbers 0, 1, 2, 3. So, they will represent binary numbers from 0 to 2 power n minus 1. Now, coming to this is not Q implies not P is the contrapositive. P implies Q is true here, it is false here. What about not P? Not P will be true if P is false, it will be false when P is true. What about not Q? If Q is false, this will be true, if Q is true, this will be false. And when is the implication false? When the premise is true and the conclusion is false. So, in this case it will be false, 1 and 0. If the premise is false, the conclusion will be true, the result implication will be true. If the consequence is true, then also it is true. Here both are 1, so it will be 1 or true. 1 represents true. So, you see that these two columns are identical, and so P implies Q is the same as saying not Q implies not P. Many times you will make use of such statements. For example, if a prime number is not a perfect number. So, you may say it as if x is a prime, it is not a perfect number, or you may also say a perfect number is not a prime. It is saying the other way around in the contrapositive manner. Okay. So, next thing is equivalence. You also have a logical connective equivalence, which is denoted by a double arrow with arrow like this. This is called equivalence. This is read as P is equivalent to Q, or P if and only if Q, or P is a necessary and sufficient condition for Q. Generally, you read it as P is equivalent to Q or P if and only if Q. This is also correct, P is a necessary and sufficient condition for Q. When is this compound statement true? This compound statement is true when both P and Q have the same values. When both of them are false or when both of them are true, the compound statement takes the value true. If one of them is false and the other is true, then it takes the value false. So, this is the truth table for equivalence. Those who have learnt a little bit about Boolean algebra, you will see the similarity between propositional logic and Boolean algebra. In Boolean algebra, you also study about two operators NAND and NOR, that we will not study in logic. Instead, in logic we study equivalence and implication. Now, let us take some examples. Construct truth tables for Q and not P implies P, and P and Q are not or is equivalent to P. So, as I mentioned to you earlier, when you have k variables, there will be k columns for each of the variable, then some more columns, but there will be 2 power k rows representing the assignments, and they will be representing binary numbers from 0 to 2 power k minus 1. Now, let us draw the truth tables for these two expressions. Q and not P implies P. There are two variables P and Q, so there will be two columns for them, and you will give the value 0 0 1 0 0 0 1 1 0 1 1 for them. Then not P, Q and not P, then the whole expression Q and not P implies now when is not P true? When P is false, not P is true, and when P is true, not P will be false. And the ending of that, when you end, when both of them are true, this is true. In other cases, it will be false. Now this is the premise and this is the consequence. When is the implication true? When the premise is false, the implication will be true. And in this case, the premise is true and the conclusion or the consequence is false. So in that case, you know that it is false. So this is the truth table for Q and not P implies P. Now let us take the other one. P and Q or not R is equivalent to P. There are three variables P, Q, R. So there will be three columns for them and there will be all possible assignments for them. That will be 0, 0, 0. Usually you write them in this order so that they are representing numbers 0, 1, 2, 3, etc. One zero one, 1 1 0, 1 1 1. Now what is the statement? The statement is this, I will write here, P and Q are not R is equivalent to P. So next you must have a column for P and Q, you must have a column for not R. So when is P and Q true? When both of them are true. When one of them is false, it will be false. So you get this for P and Q. When is not of R true? When R is false, and it is false when R is true. So you will get 1 0 1 0 1 0 1 0. Now you have the expression for P and Q are not of R. You are R-ing this and this. When you are, when one of them is true, the result is true. So when one of them is true, it is true. When both of them are false, it is false. When one of them is true, it is true. When both of them are false, it is false. In these cases, in this case it will be true, in this case it will be false, true and true. Then the last column is like this, P and Q are not R, this is equivalent to P. When are two expressions equivalent? When they take the same value 0 0 or 1. So you have to compare this and this. When they are the same, it is true. Here 0 0 it is true, but here it is 0 and 1, so it is false. 0 and 1 it is false, 0 and 0 it is true, 1 and 1 it is true, 0 and 1 it is false, 1 and 1, 1 and 1 true. So this is the truth table for P and Q are not R is equivalent to P. So for given any expression, you can draw the truth table and find out when the whole expression will be true and when the whole expression will be false and so on. Now, a tautology is a propositional form whose truth value is true for all possible values of its propositional variables. Sometimes an expression may be such that always it takes the truth value true. For example, P or not P. Consider this expression P or not P. There are two possibilities, P can be true or P can be false. When P is true, this compound expression is true because one of the components is true. When P is false, not P will be true. So, this compound expression will be true because one of the components is true. So, whether you give the value 0 or 1 or false or true to P, this compound expression is always true. Such an expression is called a tautology. A tautology is a propositional form whose truth value is true for all possible values of its propositional variables. The other way around, a contradiction or an absurdity is a propositional form which is always false. Take this expression P and not P. There are two possibilities, P is true or P is false. If P is true, not P is false, so this expression will be false because AND will be true only when both of them are true. It is not possible for P and not P to be both true, either one of them will be true. In any case, one of them will be true, the other will be false. The possibility is this is true, this is false, or this is false, this is true. In any case, this compound expression P and not P will always be false. Such an expression is called a contradiction. A propositional form which is neither a tautology nor a contradiction is called a contingency. These examples which we consider, Q and not P is equal to implies P, and Q and P are not R is equivalent to P. These two are examples of contingencies. Some cases they are true, some cases they are false. So, they are examples of contingency. Given a propositional form, it is always possible to find out whether it is a tautology or not, because you can always draw the truth table, and if the last column is always 1 1 1, then it is a tautology. If the last column is always 0 0 0, it is a contradiction. Sometimes it is 0 and sometimes it is 1, then it is a contingency. Then we have lot of logical identities. These logical identities can be used in simplifying logical expressions. Look at this one by one, let us see one by one. P is equivalent to saying P or P. When you say P or P, it is not necessary to say it twice, it is enough to say once. This is called idempotence of R. Then if you have P and P, it is not necessary to write like this, it is enough to say like this. So, P is equivalent to P and P, this is called idempotence of AND. So, whenever in an expression you get something like P and P, you can replace it by P. Then you have the commutative laws, it is equivalent to saying Q or P is equivalent to saying P or Q. You can interchange the variables, does not affect the meaning. This or that, A or B is B or A. So, P or Q is same as Q or P, this is called commutativity of R. Similarly, you have commutativity for AND. P and Q is equivalent to saying Q and P. And you have associative laws, P or Q, then R R. That is, first you R P R Q, then you take R and combine, that is equivalent to having P R Q or R, and P and Q and R is equivalent to saying P and Q and R. This is called associativity of AND. In general, we are whenever you write an expression, you try to use parenthesis. there is no priority, but generally not has higher priority than and then or. If you use only these three of them, not has higher priority than and then or, because you can write not P and Q. This is not P and Q, that is equivalent to saying not P and Q. You can write without that parenthesis. It is not P and Q. This is different. If you want to write like this, you must put the parenthesis in a proper way. So, we see that, but P and Q and R you can write without parenthesis because of associative. Whether we group this first or group this first is immaterial. When both the operators are and, without any problem you can write like this. That is what is meant by associative and similarly for all. Whereas, you can realize that P implies Q implies, if you want to write like that, P implies Q implies R. This is different from saying P implies Q implies R. You cannot say something like this, P implies Q implies R, because you do not know whether you mean this or that. You can draw the truth table and verify that this has got a different value, this has got a different one. They are not the same. So, you cannot write something like this. You have to put parenthesis wherever is either you mean this or you mean that. So, implication is not associative. Then there are De Morgan's laws, which are very common and very useful also. Not of P or Q, you can bring the not inside and that will mean not P and not Q. You can again draw the truth table for this and see that they will be identical. The columns representing them will be identical. So, when you bring the not inside, R becomes and. Similarly, not of P and Q will be not of P or not of Q. So, when you bring the not inside, and becomes R becomes and. These are called De Morgan's laws. Then you have distributive laws and distributes over R, that is P and Q or R is equivalent to saying P and Q or P or R. So, you can distribute and over R and write like this. Sometimes you can use the distributive laws in the reverse direction also. Another thing is R distributes over and P R, Q and R is the same as saying PRQ and PRR. Again here also the distributive law sometimes you can apply in the reverse. Then you have these rules implying when one of the operands is true or false, PR1 is always 1. So, this is a compound statement, but when one of the operands is true, the compound statement is always true, this we know. So, even when one of them is true, this is true, and now we have taken one operand as true only, so this is 1. P and 1, if P is true, this will be true, if P is false, this will be false. So, P and 1 has the same value as P. Similarly, for R, PR0, if P is true, this will be true, if P is false, this will be false. So, PR0 takes the same value as P. And when you AND with a 0, P and 0, because one of the operands is false, the compound statement will be false. So, you will have P and 0 is the same as 0 or false. P or not P is always 1, always true. This is called a tautology. This is what we have seen earlier. P and not P is called a contradiction or absurdity. It always takes the value 0. And you have double negation saying P is equivalent to not of P. So, if you use negative negation operation twice, it is equivalent to the original statement. There are some more statements like this. We shall briefly look into them. We shall look into them in more detail in the next lecture. but just we have a brief look at them. P implies Q, you can write it as not P or Q. This is equivalent to saying P implies Q. And similarly, P is equivalent to Q, you can equivalently say it as P implies Q and Q implies P. This rule is also true. P and Q implies R is equivalent to saying P implies Q implies R, and P implies Q and P implies not Q is equivalent to saying not P. This is called absurdity, and this is used in proofs by contradiction. This is the most commonly used. This we have seen earlier. P implies Q is equivalent to saying not Q implies not P, which is the contrapositive, so on. So, this class we have learnt a few logical connectives and how to write the truth table and so on. We shall continue with these concepts in the next lecture.